welcome everyone, those in Mountain View and those around the world, especially those in Asia who got up early to attend this talk. I am Shuming Jai. I, like many of us, devoted most of their life career to study ways of entering text onto computers. So we are, in a way, we like to think we're making history today. I help to lead the Gboard team. Gboard has 1 billion active users, works in 900 languages and language varieties, including Chinese. We're mostly motivated by the needs to communicate over mobile devices. It turns out that there's another history to this, to what we do today, that is how you enter Chinese into computers, to use Chinese as the primary medium for human-computer interaction. And there's actually a long history on this, and there's no better person than Tom who could tell us that story, because he did the original research over at least a decade of time. So Tom is a professor at Stanford. He specialized in the history of technology and history of Chinese and Chinese culture and language. About 10 years ago, he came to Google to give a talk on his now famous book called The Chinese Typewriter, which won the Fairbank Prize. Before that, he wrote also a very influential history book on the classification of Chinese ethnic groups. After that, he published many other books, including Where Research Begins and Your Computer is on Fire, and so on and so forth. And this month, he releases yet another book called The Chinese Computer, which happens to be the month of Asian and Pacific Heritage Month. So it's very fitting. And please join me in welcome Tom Mullaney.
Welcome to everyone joining online, and thank you so much for coming out today. Today is actually the birthday of the book. Today is the official day of its release, so it comes as a real joy because, as Shuming noted, this is the completion, I suppose, of a project that dates back now 16 years. If you have ever doubted your commitment in life and whether or not you should be dedicating yourself to the study of inputting text in digital devices, just imagine what it's like to dedicate a third of your life so far on Earth to the history of that. So this dates back 16 years, these two projects. And now with the Chinese computer coming out, it kind of brings a close to this history and my engagement with it. The Chinese typewriter, which I had the honor of coming 13 years ago here at Google, basically begins in the 19th century with the advent of electric telegraphy, and a similar question to what we'll discuss today: how do you fit Chinese with tens of thousands of characters, no alphabet, within the context of Morse code, something that too was built with the Latin alphabet in mind, all the way through the contemporary period into the era of computing. And so I want to start the discussion today with an episode that, just briefly with an episode that basically launches the book. The introduction begins here. It is a Chinese typing competition from 2013 in Henan. So it's a shurufa competition in which different contestants sit down at standard off-the-shelf Windows machines. They are presented with a series of texts in common, and then each of them vies to be the most accurate and rapid inputter of these passages as possible. I know that no one in this room needs an introduction to this, but in case anyone comes across this on YouTube or elsewhere, it's been really delightful to see the response to the first Google Tech Talk in the comments field, and sort of have met actually many people by way of the comments field of that particular video. But let me just show you in a nutshell what what input looks like in a Chinese context circa 2013. So the text you see at the top of this is the text that is to be transcribed. This is part of the random character sequence. If you read Chinese, you'll see that this is sort of, I'm sorry, this is not the one. This is the actual text, excuse me. There's another part of it that is the random sample, in which a random assortment of individual Chinese characters are presented. In this case, there are compounds and so forth that are there. But what you'll see at the bottom then is the composition window. One of the core basic dimensions of Chinese human-computer interaction and all human-machine interaction in the digital environment is the multiplicity of screens and this feedback loop that is not at all common in the Latin alphabetic environment, which is there is a composition window, that is the window where you are producing whatever text you're producing, and then there is the pop-up menu, this sort of interware or application that as you are entering keystrokes on the QWERTY keyboard, this little pop-up menu is following the cursor along, and based upon whatever you have provided to the input method editor, is dynamically making suggestions to the user about what Chinese character or characters you might be en route or trying to produce. This pop-up menu has a deep history. I'm excited to show you the first ever pop-up menu in history, which was not a computer application, it was a physical device. But we've always had a split screen in Chinese human-machine interaction, the composition window, and then this cybernetic feedback loop pop-up menu that has been core to that process. In the course of doing this, you'll also notice, and this is relevant, let me go ahead and maybe try that again and start it one more time. You'll notice that in this particular context, the letters that are being inputted on the QWERTY keyboard, every one of the machines in this competition is, again, off-the-shelf Windows machine, are not phonetic. If you actually stop this, you'll notice that the competitor from whose screencast this is being taken is not spelling out the sound of Chinese characters. Instead, he's using the letters of the Latin alphabet to describe the structural shapes and features of Chinese characters, so-called structure-based input systems. One thing we'll discuss is that although today phonetic input, Hanyu Pinyin input, is dominant in the Sinophone world, that's a very recent phenomenon. And from the advent of the very first Chinese computer in 1959, throughout the 60s, throughout the 70s, throughout most of the 1980s, Chinese engineers and engineers around the world considered phonetic input to be the worst of all possible options, and far worse than many of the leading structure-based input systems, where you're using A, B, C, D, E, F, G to describe the strokes out of which a character is built, the bushou, or radicals out of which they are composed, and so forth. In this case, the competitor is using wubi, or five-stroke input, which today is still used, but by a minority. What's fascinating about this, and I'll sort of put my cards on the table here, is that the winner of this particular competition in 2013 clocks in at a recorded 221.9 Chinese characters per minute, or 3.7 Chinese characters per second. I do the math in the footnotes in the introduction, but no matter how you cut it and no matter how you determine what the character to English word ratio is, we have some reliable statistics based upon basically translation. This will defeat the topmost Guinness Book of World Records English typist in the world. This is faster than the fastest English typist. That is not because the winner in this case is nom de guerre as you should. That's not because his fingers are built in a different way or that his neural pulses are operating faster. It's because the upper ceiling, the maximum kind of informational ceiling of the underlying logic of Chinese input is higher than the overall ceiling of the maximum speed of typing. So input and typing are not the same thing. We call them a Chinese typing competition, but it's really a Chinese input competition. And we'll talk about that. So the question then is, if you go back, if any of you read the Chinese typewriter, you'll know that most of the technologies that are being discussed there, Chinese telegraphy, Chinese typewriting, but also character retrieval systems for dictionaries and stuff, they are maxing out at maybe a few dozen characters per minute, maybe 25 characters per minute, maybe with certain innovations that I'll discuss, 35 or 50 at the max. By far the slowest of the global scripts and world languages on the scene, nowhere close to Latin alphabetic systems. How do we get from that moment to this moment of 221.9 Chinese characters per minute? What does that look like and how do we get there? The abstract of this particular talk raises this question, and I'll give you the English translation in a moment, but it is what I describe as this audacious claim that is made by a number of Chinese engineers in the late 1980s, which offer up an incredibly optimistic view of what the future holds for Chinese human-computer interaction. And here's the translation. At present, input speeds for modern Chinese have clearly already surpassed speeds for Western languages. This is in 1989. Into the future, as character and compound or ci-based processing undergo even deeper research, and as even more ideal character libraries, these are little language models, by the way, of even higher quality are created, we have every hope that users with leisurely keystrokes will be able to reach or greatly outpace the speed of human speech. This is in 1989. This is actually at a time when Chinese input at scale is not as fast as Latin alphabetic input, but people have already seen in the data and in usage the possibility that lies ahead. Now contrast this with a statement made in the exact same year by the leading Western linguist of the Chinese language, the sort of father of many of the great linguists that now have jobs at Adobe and Apple and other places, John DeFrancis, who wrote that effectively Chinese input was doomed and could never, ever reach anything like the supposed immediacy of English. In word processing, we normally input alphanumeric symbols and print out text expressed in the same symbolic code. I see the letters QWERTY on my keyboard. When I type them, they come out the same. This is very simple and highly efficient, especially when the operator is a skilled touch typist. There is not, and I believe never can be, as efficient a system for inputting and outputting Chinese characters. So these are strong words on both sides. And with great respect to the late John DeFrancis, he was completely wrong. That we have evidence that the first of these two prognostications seem to be bearing out and the second is not. And so what does this mean? Where does this come from? This is not a quote. This is sort of a synthesis of another passage by the Chinese engineer Qi Yuan, who around the same time tries to map out, try to give some flesh to that earlier quote by one of his colleagues, flesh out what he imagines to be the phases of development of Chinese input. And he breaks this into 4 phases. The fourth of these, to give away the ghost, is what sets the stage for a bridge to generative AI and for prompt engineering. I'm going to try to make the case that China and Chinese computing has been prompt engineering for about 60 years now, while prompt engineering is something of relatively recent and shocking vintage to the Latin alphabetic world. The first of these is the character, just the challenge of how do we get a single character into a digital device? That's a challenge. How are we going to do that? The second of these is, and once that's solved, the second is the compound. Most modern Chinese is not built out of single character semantimes. It's built out of 2-character words. 学生, 大学, 国家, whatever it might be, 2 characters that then translate into a meaningful word. And if we could exploit that aspect of the Chinese language, we could accelerate the process of input. And once we attack and tackle that problem, we can then move on to longer passages, the sentence, the jiu. This could be chengyu, idiomatic expressions. It could be diming, toponyms. It could be phrases. It could be anything that we have in our ciku, our character repositories. And once we tackle that, we move on to the fourth and final phase, which is writing itself, wen. And so he maps out these 4 phases, the zi, the ci, the jiu, the wen. And he imagines it kind of moving through phases. And at this moment in time, and then we'll back up in time, at this moment in time, he said, we've already tackled the first two of these. We're already on to phase 3 in the late 80s. So we'll begin with the character, because it's not at all self-evident that this should be possible. This should be possible to do. So the first challenge or obstacle that we face is that by this moment in time, we are in the era of the keyboard. The keyboard is an emergence from post-US Civil War precision engineering. Think of Remington rifles, Remington typewriter, Smith & Wesson, Smith Corona. These are not accidents. These are quite literally precision engineering firms and manufacturing units that in the wake of this cataclysmic conflict no longer have the same orders for weaponry, and will begin to move their systems of operations over to other forms of precision engineering, like see later bicycles, but also sewing machines, and this newfangled invention, the typewriter, a machine that allows you to write with type. Okay, so movable type, but we don't want 10 copies of E and 2 copies of X. We want 1 copy of every letter, and we want to be able to write with type. Now, I talk about this in the book, The Chinese Typewriter. I won't revisit it here, but in the early years of the typewriter, there was no single typewriter. There were many, 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 many different ideas about how one should build such a device. There were typewriters that had the keyboard that we know, the single shift Remington-style keyboard. There were keyboards that were out there that had double the size with both capital letters and lowercase all on one interface. There were typewriters that had no keyboard at all, index machines where you move basically a pointer over top of a guide, and then a corresponding type mechanism will bring the type into printing position. There are famous typewriters that are manipulated with one hand. It was sort of a weird, wild west of human-machine interaction exploration. Over time of the 1870s, 80s, 90s, this sort of rich and weird ecology of starting points of the typewriter collapses to the technical monoculture that we have today, which is the single shift keyboard typewriter. The single shift keyboard typewriter represents one of the greatest collapses in technological imaginations that the modern period has ever seen. And what we're left with is a few exceedingly dominant companies like Remington, but then others like Smith who get on the bandwagon of the single shift keyboard. And soon, very quickly, with a few minor exceptions, we have the single shift keyboard is the starting point for all human text technology interaction. Now, for French, that's fine, because all you have to do at the manufacturing plant is replace the key surfaces and replace the type. For Cyrillic, that's pretty easy. You, again, remove the key surfaces, you retrofit the type. For Hebrew, it's okay. We have to view a few things. We have to change the keyboard surfaces. We have to change the type, and we have to adjust the type and carriage return mechanism. But voila, we turn an English machine into a Hebrew machine. As we begin to move outward from self-sameness, ipseity to alterity, though, the problems get harder and harder. And I put the harder in quotes because, as you could see, this is a relational concept of difficulty. Arabic is not harder than English. Arabic has an alphabet. The Arabic alphabet is roughly the same size as the Latin alphabet, but the Arabic alphabet connects, and the shape of the letters change depending upon their context. Remington can't handle that. And so the Arabic problem becomes that kind of problem. Korean becomes a problem, not because there's no alphabet, there is, but because of the pachim, this piece that can stick onto the bottom of the graph, and we don't have that in the Latin alphabet, so it's a problem. Eventually, through various sort of ingenious workarounds, and quite literally colonial violence that is visited upon many of these writing systems, where they're just said, you've just got to cut out letters. Burmese has letters cut out, Thai has letters cut out that are low frequency. We reach the water's edge of Chinese. Remington fails to break into the Chinese market. IBM fails to break into the Chinese market. Olivetti and a variety of others, for the simple reason, not that it's inconceivable, as we'll see, to build a typewriter with a keyboard for Chinese, but because they would have had to change their entire manufacturing plant. They couldn't just tweak it. They would have to blow it up and start over again, and they had absolutely no interest in doing that. And so the first Chinese typewriter we end up having, which will become important for us, is a machine that has no keyboard, a typewriter with no keyboard. And the way one manipulates this or uses this is you see the knob, the green knob in the front, you hold your left hand to that. If you move left and right, the entire tray bed moves. On the tray bed are a series of 2,450 35 by 70 potential characters, each one a metal slug, kind of like movable type. If you take, they're all loose. If you take this tray bed, take it off the machine and do that, they will dump out onto the ground. With your right hand, you see that sort of circular device. Let me see. Oh, I do have my cursor right there. You hold that with your right hand. You can move it left and right and forward and back. And so what you're doing is you're bringing this type mechanism, this rectangular object right there, over top of the character you want. When it's over top, you push down on your right hand, a little metal finger kind of pops the slug out. It gets locked inside the chamber. It rubs against the ink circle, which there in this is white. It's not inked. And then it's inked and strikes the surface of the platen. There's no paper on this, but there would be paper. And then it falls back to its original position, and the force of the snapback will pop it out back into the empty hole that was left behind. Okay, so this is a diagram from the year of what this looked like. Now, this is something to sort of look ahead. We're worried about how we would digitize something like this is where we're going. But there's already inklings of where the second phase of this history is going to be solved, because even in the era of Chinese typewriting, everyone knew that modern Chinese is full of these two-character words. And so when you were learning to study a Chinese typewriter in school, you would practice these sort of diagrams of language. 学生, 学生, 会员, and you would have to sort of walk the tray bed into existence and over time. And so these are, I diagrammed out the opening few characters of a 1930s device, for example. So you're kind of warming up your familiarity of the layout of this, okay? And then this happened. Circa 1947, a prototype experimental Chinese typewriter with great fanfare was announced to the world, under development for about a decade and a half by this man, Lin Yutang, leading kind of almost cultural ambassador, writer, sort of quasi-linguist, but not quite, best-selling author, etc. And that's his daughter, Lin Taiyi, on this machine. It's called the Mingkuai, the clear and fast typewriter. And here we have, for the first time, a Chinese typewriter with a keyboard. How in the world does that work? I don't see 80,000 keys on that keyboard, but it looks just like pretty much a Remington, or basically the same chassis. The key here is that unlike Remington and Olivetti and many other people that were thinking about building typewriters, Lin's pathway to the question of inscription was through the question of search. He spent the 1920s doing many things, but one of the things that he did was take part in this thing called the 简字法问题, the character retrieval problem, the character retrieval crisis. This was like this storm in a teacup among early Mingguo Republican era Chinese intellectuals. And the big question was not typewriters, or obviously not anything like computers, but dictionaries and filing cabinets and phone books and name lists. How do you retrieve Chinese character information from a database with a speed and efficiency that our Latin alphabetic brothers get to enjoy and take for granted? We have the Kangxi Bushou, the radical stroke system. They're deriding it as complex and slow. And there's this crisis, this fear that quite literally at an informational level, we are behind. It takes us 30 seconds to find something that someone else takes 5 seconds to do. He brings this idea, unlike all of these other individuals who you see up here who are participating in this and proposing different ways to retrieve things. He will take his idea of a 简字法 and turn it into the world's first 输入法. He will take retrieval and search and make it search writing, writing with search, writing through retrieval. So when you would sit down at this machine, this is Pearl S. Buck, a family friend, actually, the recipient of this from Lin Yutang, the picture of the baby. When you sat down at this machine, And it'd be very, very strange if you were used to a Remington. You would start pushing keys, nothing would happen. There would be no characters on the paper, but you would hear mechanisms moving inside. Then you might push a few more keys. Still no ink on the page, but what you would notice in this little rectangular thing right here, the world's first pop-up menu, you would see up to 8 character candidates, Chinese character candidates that match basically the criteria that you had provided. This criteria was actually the thing that Lin Yutang spent the most time working. These are patented proprietary symbols that he made. Some of these resemble Chinese character components, and some of them do not look at all like Chinese character components, because what he's trying to do is come up with a structure-based, he wouldn't call it this, input system, whereby the depression of any 2 keys would result in a possibility of up to, but no more than 8 possible matches in memory. The memory was physical, like metal. This is a metal character database. This complex system of kind of like Ferris wheels inside Ferris wheels inside Ferris wheels. This is what's moving as you push this button. And then you would have the final set of 8 that are provided to you. And then the final keystroke would be the number 1 or 2 or 3 or 4 or 5 or 6 or 7 or 8. Similar to the way we do on an input system where you choose, yes, that's the character I want. Now this machine is never mass manufactured. It comes, it's sort of ill-fated. He releases it shortly before the Chinese Civil War concludes with Chinese Communist victory, the Cold War mindset, but also a general incredulity, a sort of difficulty in swallowing the concept of this by potential manufacturers like IBM. And so this will basically die in obscurity from that point onward. But the concepts that he had created live on and become the entire logical basis for all Chinese computing to this day. I'll jump over the IBM story. The IBM story is really fascinating. It's what chapter 1 is all about. But this electric Chinese typewriter released around the same time, similar concept. There's no Chinese characters on the keypad, as you can see, just numbers. And inside is yet another metallic metal drum of Chinese characters. But instead of little pieces of Chinese characters on the keyboard, what the operator is using is effectively the Chinese telegraph code, this system of 4-digit ciphers, 9,999 4-digit ciphers from 0001 to 9999. And the operator literally had to memorize all of these 4-digit ciphers. And you would enter them in, and then it would retrieve that from memory. Now, where we get to computing is in the 1950s, when, aware of the work of Lin Yutang, aware of the work of IBM, a professor of electrical engineering who spoke not a single word nor wrote a single word of Chinese, Samuel Caldwell, student of Vannevar Bush, advisor to David Huffman, basically became enamored of the question of Chinese by dinner time conversations with his overseas Chinese students at MIT, just like chit chat, you know. And in the course of that chit chat, some elements of Chinese writing that he had not been aware of came to the fore, such as stroke order. The idea that if you take 5 Chinese people and you give them the same Chinese character, they will write it in the same order, on their separate pages. So he thought that since there's no alphabet, that there must not be a sequence to the way that one writes. And the student who goes on to be a core research associate with this says, no, of course there is. There's an order. And as a great student of logical circuits, and he says, wow, in that case, you could build a logical circuit for this, in which the goal is not to compose the character, but to find it in memory by an address. And the address would be effectively the spelling, so to speak, of the word. So with various research at the Graphic Arts Research Foundation, basically a center that was a nonprofit developed for the advancement of photo typesetting, this World War II French and then American innovation, he sets about the creation of Sinotype, or the ideographic encoder. And you can see on this machine, the second pop-up menu in history. So you have a composition screen, and then you have the thing that is checking that the address you have given it, in fact, leads to the character you actually want, and you have another chance to then commit that to the photographic master. Over time, this composition, this pop-up menu will continue to be a physical apparatus, One of my favorites is actually a 1970s photograph of a demonstration of actually the second generation Sinotype in Beijing and Shanghai, in which the pop-up menu is literally a separate computer monitor, and the composition menu is, monitor is its own. And so you're constantly moving between the composition window and the pop-up menu. Eventually, as we know, these are merged programmatically to the point where these two menus become one and the same. So this is the first implementation of Chinese text processing on an Apple that was also at the Graphic Arts Research Foundation. This is Sinotype 3. And you can see that you have the composition on the top and then the input sequence on the bottom. And this is too Chinese telegraph code. That's why it's numbers. Very interestingly, one of the reasons that the developers of Sinotype 3 chose this particular model of Apple is because it was popular with gamers, where the top of the screen was really good for graphics, which is necessary for the process of the printing to screen of Chinese characters at this time. It's all rasters. We don't have any symbolic sort of notation way of doing this. But that the bottom was well outsuited basically for the menu items in popular games. So they basically hacked that or glommed themselves onto it. And instead of things like run, jump, whatever the commands were in various video games at the time, we're going to use that lower bandwidth of the monitor as our pop-up menu and the top of the screen as the composition window. So by this point, by the time that this is being discussed, we have solved effectively, at least in principle, the notion of how you get one character in at a time, but it's still exceedingly slow. We haven't broken through, we haven't broken into anything really. This is where we come back to this notion of the typewriter and how it's built and how people actually use it. Remember, back in the 30s and 40s, people are already practicing to use a mechanical Chinese typewriter by practicing, 会员, 社会主义, whatever it might be. They're learning these combinations. But still, in the 1920s and 1930s and 1940s, the tray bed, the cipan of a Chinese typewriter, is organized the way a dictionary is organized. And what that means for our purposes is it has nothing to do with natural language arrangement. So just like Apple and aardvark are near each other in the dictionary, but do not tend to go together in regular speech, you have all of these Chinese characters that are neighbors to one another that don't appear in natural language. And so somewhere along the way into the 1950s, and I'll jump ahead here, is some Chinese typesetters and Chinese printers got it in their head to play around with the tray bed, to quite literally dump out the characters of the tray bed and to start rebuilding these sort of archipelagos of character compounds that actually go together in regular speech. Now, this is a big deal because this is 2,450 factorial possibilities. There are more potential tray beds than there are atoms in the universe, right? Or something of that nature. But there's a lot of possibility here. So if you look at this one zone here, just hovering here, you have many, many, many adjacent neighbors. Remember, adjacency on the tray bed, there's no keyboard. So adjacency is speed. The closer you can get these things, the faster. You have 共同,同时, 时间, 随时, 随便. You have dozens and dozens of real Chinese words that are kind of compacted into the space. This is a tiny zone of the tray bed. Imagine doing the same principle over 2,450 spaces. They even practice on the logic of punctuation marks. Chinese uses particles for punctuation, 你好吗, 好吧. So why in the world would we put question marks next to exclamation marks and periods and commas when question marks always appear after basically these three characters, na, ma, ba? So let's just put them there. In the process, they ended up just with the era of mechanical typewriting, but then setting the stage for later digitization. They had sped up the typewriter by a factor of 3 with no electrification. So this is a heat map that indicates the general speed of a mechanical Chinese typewriter. The color white indicates that that character on the tray bed has one neighbor with which it can be meaningfully connected. Red means there are many neighbors with which it can be meaningfully connected, and black is that none of the neighbors can be meaningfully connected. This is a dictionary organized tray bed. This is a 1950s predictive text tray bed. When computer engineers who are coming of age in this era. They are used to typewriters. They're used to these kinds of typewriters. When they are jumping into this system, they are fully aware of these ideas and these approaches, and they are immediately stealing these pages from the world of Chinese typewriting and bringing them into Chinese computing. One very famous one, Zhi Bingyi in Shanghai, who very famously spends his years of his life in a Cultural Revolution era prison, and in order to not go insane, effectively creates in his mind a shurufa to keep himself sane. He actually wasn't making a shurufa, he was making an input system. He was too making a jianzifa, a character retrieval system. He's trying to imagine how to alphabetize the Chinese information world. He would write on the, he had no paper, he would secretly write on the invert side of the lid of a teacup with a pen that he kept in secret, and he would just work through various combinations of Latin letter combinations fixed onto Chinese characters in order to not lose his mind. When he was released, he was entered into basically home confinement, but then in the Reform era, he started to make inroads back into the sort of four modernizations era of China, and soon he found himself at a signatory signing with the Graphic Arts Research Foundation to get his input system onto the Sinotype 2 and the Sinotype 3. Now, for our purposes, what's important here is not that the input system was able to input one character at a time, but now we're able to enter two characters at a time. So he had, his was a structure-based input system, like Lin Yutang before him, but he had this special part of his code, which was dedicated to compounds like the ones that you see here. And that special part of the code was the only part of the code that used phonetic values for the input. So imagine that you had anxuan, like safety. In his code, if you were to enter an by itself, there is a sequence of Latin alphabet letters that describe the shape of that character, an. And then if you were to enter quan by itself, you would have another set of Latin letters that describe the shape, the structural shape of quan. But if you enter anquan as one compound, all you need to enter is AQ. AQ, the first two letters of the Hanyu pinyin value for that. The great thing is that there is no legal or valid Hanyu pinyin sound of AQ. There's no way for the computer to be confused about what you're after. There's no ambiguity in it. And so the use of these abbreviations proved to be really, really fast. Now, at that time, that was just sort of a shortcut. It wasn't the main ingredient, but engineers were looking at this and saying, this is worth our investigation, worth our exploration. And so what you end up having are effectively phases 2 and phases 3 of the compound, and of the ju, the sentence, kind of happening in tandem with one another, this predictive text and shortcut. So this is a this is a diagram of the computer monitor from the 1980s. And what's important about this is this system is both using Hanyu pinyin shortcuts, like double letter shortcuts for the inputting of ci, compounded with this thing called connected thought suggestions, or lianxiang zi. You can see it at the bottom. So if you go over here, this is again the composition window. Down here is effectively the pop-up menu. So this person has already entered the character, the term People's Republic of China, 中华人民共和国. But the last character that they have input is guo, country. And so instead of now the input system kind of taking a break and being like, okay, I'm just going to wait until the inputter like starts the process again, the inputter gets to, the IME gets to work immediately. It says, well, the last character that I just received is guo. Let me start making predictions about the next most likely character in the sequence. So you have jia, which would be guojia, country, guofang, national defense, guoji, international, guonei, domestic, guowai, international. And it's trying to, based on statistical frequency, make the next likely guess in the process. This is the 1980s. It even below has these lianxiang ci, ciji. So these are suggested connected two-character compounds that might follow the word guo, the character guo. This term, lianxiang, is fascinating in two ways. One is that the term is coined in the era of typewriting. These natural language sort of predictive text layouts of the tray bed are called lianxiang. And there is a major Chinese company that ended up buying out IBM at one point in its history. You know it as Lenovo, and its Chinese name, of course, is lianxiang. That's how important this concept is. And if you read the autobiography of the founder of it, this is not an accident. This idea of connected thought as being so core to this by the 80s. This has now become exceedingly powerful, of course, both the shortcut method, which is very, very, very common in everyday usage, but also the ability to have long strings of these pinyin shortcuts throughout the process. Now, from here, we start to enter the stage, and then I'll accelerate, of longer and longer passages. And very importantly, is that input in the early 2000s enters the cloud. You start to have yun, shurufa. And so now all of this stuff that used to be localized to the individual computer on one's desktop becomes a distributed feature. So think of the Google search bar. Think about when it became possible for the average user not to only enter their search, but to start to see an auto-populated set of things based upon, what's in the news that day or what other people are searching for. Take that and put it in Microsoft Word in 2012. This is way far in advance of the stuff that we start to see in the Latin alphabetic world. And the corpora that this thing is able to map against and retrieve against is getting richer and richer and richer. And one of the examples that I use in the book is one of my favorites of XMYJJ, which has no Hanyu Pinyin valid thing, but will retrieve for you, if you have cloud input turned on, the opening stanza of one of the most important and beautiful Tang poems in history. Xiama Yin Junjiu, so parting, bie. Now, this is a very famous poem, so of course you would find it in a dictionary, but as I make the joke in the book, imagine typing in a comparably famous passage of Shakespeare, just the first letters of the Shakespearean soliloquy, and see if your computer knows what to do with it in this realm of IME. This is how we get to over 200 characters a minute, is all of these things are operating, with the exception of yun shurufa, that's disallowed in the competition. But if you watch this screencast at frame by frame, because it's so fast, you actually have to slow it down to see what the heck is going on. You'll see all of these kind of strategies and operations in the pop-up menu all happening at the same time. And this is what's fascinating. If we think back to the quote from John DeFrancis, it kind of understand where DeFrancis is coming from. The idea of a composition window and a pop-up menu and like special codes that you have to use. This sounds very cumbersome. Like there are many hoops to jump through. There is no way that this could ever achieve the efficiency, the speed, and the accuracy of immediate input. And you can't fault someone for imagining that. And yet here's the evidence that surprisingly, by adding additional layers of mediation in the human-computer, human-machine interaction, counterintuitively, you can radically accelerate the process of getting text into digital devices. So what the book ultimately is about is the question of what do we call this? Not to what do we call Chinese. This is a passage from the random character section, by the way. But what do we call this? This passage on the bottom is what the winner of this competition actually typed on his keyboard. That's what he actually typed. This thing above here is the secondary transcript that has been translated from this primary transcript into something like Chinese. So what do we call this kind of writing? I spent a long time trying to find a word out in the wilderness in various disciplines, obviously within linguistics, to try to find, is this abbreviation? Is it shortcut? Is it like emojis? Is it like this? And it turns out that none of these terms, dozens and dozens and dozens of them, really fit the bill. And so ultimately, something that I did not want to do, but I ended felt like I had to do, was try to give this a name, and the name that I give it is hypography. This idea of almost like, hypothyroidism, there's something that's operating sort of below the level of the graph. So think of hypertext, this is hypotext in some sense. And the features of hypography that we have here is there's no one-to-one relationship between keys and graphs, which departs from the Latin alphabetic Remington model. There is this built-in, almost necessary recursive property of the pop-up menu and this sort of check-in candidate loop. Ironically, the primary transcript of human-machine and human-computer interaction is disposable. The second that it achieves its goal, it's supposed to be discarded and replaced with a secondary transcript. There are a theoretically infinite number of ways to map input onto output. So in English, if you're just typing the cat bit the dog, there's only one way to do that correctly without typos. In mainstream sort of typing, there are a theoretically infinite number of ways, and in practice, over 1,000 different shurufa that have been invented since the 1950s. And that successful completion of the graph does not depend upon completing the input sequence, because what we're doing here is we're not writing or composing, we are retrieving. And the second we have a match, we don't need to look anymore because we have our match. Now, there is hypography in the Western Latin alphabetic world. It's called stenotyping. The reason that stenotypists can achieve faster than the speed of human speech in courtrooms and in boardroom meetings is because they're not using a Remington typewriter, which is impossible to capture the speed of human speech. They're using this special device that captures a primary transcript that then needs to be translated into a secondary transcript, which is cumbersome. It adds an extra level, but what it buys you is the ability with a single chorded keystroke to say objection, overrule. That's one keystroke on a court stenographer. You're not typing out those letters. It's a single chord depression. But you then have to go through the process of translating this primary transcript into a secondary transcript. There are some other places that we have since forgotten about in the history of Western computing where something like hypography was contemplated. The famous mother of all demos, which gives us, hyperlinks, gives us the mouse, gives us video conferencing. All of these things that we imagine are like that he just saw the future of the world. There's one thing that we all forgot, which is he offers the chording keyboard again. And he says it's as important as the mouse, but it was forgotten from history. And credit to a brilliant student of mine at Stanford who went into the papers and found that. The Palm Pilot, the Palm alphabet is a form of hypographic writing. As soon as you make that stroke and it then retrieves the letter A from memory, you don't need the thing anymore, you move on. But the thing is that in the Latin alphabetic sort of Western context, these are isolated to specific zones of usage. Court stenograph, T9, the Palm alphabet, but there's always this normal mainstream default idea of immediate typing. In the Chinese context, and for that matter, Japanese, Korean, many South Asian scripts, hypography is the rule, not the norm, and there is no alternative to it. And so conservatively, on an average sort of year or day, the number of hypographic symbols that are produced in the Sinophone digital world, I sort of did a rough back of napkin estimate that in a year, it is equivalent to if you were to print it out, like actually print out the primary transcript, it would be the size of the Library of Congress and its holdings. And it's destroyed the second it achieves its secondary transcript. And so this notion, just to conclude, and then I'm interested in hearing people's thoughts, is last spring, when ChatGPT sort of, jumped onto the world scene, and people were trying to wrap their head around this concept of the prompt and like prompt engineering that, first of all, what is this mode of human-machine interaction? What is it in this world where there are different qualities and strategies of prompts? From my standpoint, as an historian who has spent, a decade and a half studying Chinese input, it's like China has been prompt engineering since the 1950s. And I don't mean China in the national sense or ethnic sense. These are engineers from all around the world gravitating to this wicked hard problem with Chinese input. But all of the features of hypography are there. What you type is not what you get. The primary transcript of the prompt is disposed of the second it produces the thing that you want. The one difference between a kind of generative AI mode of prompt engineering is we have lifted the speed limit of input. The speed limit of input has always been the speed limit of human intention. I'm trying to get my thought on the page as quickly as possible. Can you keep up with me? Once we remove that speed limit, then the question becomes, can you produce text that is in the spirit of what I'm after, but that I have not yet committed myself in my human will to produce something that I haven't even foreseen yet? And at that point, we we are starting to move into the realm of 1,000 words per minute, 1,500 words per minute, 2,000 words per minute, to the place where words per minute ceases to have any meaning at all. And so as I watched all of these various ads, weird new job alert, what is an AI prompt engineer, these various courses on prompt engineering and so forth, realized that going all the way back to the migration of Jianzifa, the character retrieval to input, going through the hundreds and then over 1,000 different shurufa that were invented and tested from the period of the 1940s into the 1980s and into what we have today, that every prompt and a way of thinking about what prompts are is that prompts are hypographic. Prompts are forms of hypography. Hypography has existed for a long time, but in one zone of sort of human linguistic experience, it is totally mainstream and normalized. And in another zone of human kind of linguistic and human-computer interaction experience, it is at the fringes, it's optional. There's always a default we can come back to. So I want to hear your thoughts and any questions, and I look forward to it. Thank you so much for having me.
Thank you for the talk. It's fascinating. I'm curious about how the typing speed nowadays looks like. Like you mentioned that it's like 300 something characters per minute when you're in Wubi. Maybe that's Wubi, right? How about pinyin today?
So the latter parts of the book, especially the last sort of chapter and a half, addresses the rise of Hanyu pinyin based input, which is of course dominant today. And the answer is that there is a trade-off, that the sort of maximum capacity in some senses of phonetic input is lower than the ceiling of structure-based input. So when you should, again, his nom de guerre wins in 2013, he's winning with Wubi, and he is up against competitors. Some of the competitors are competing in pinyin, and you see this actually pretty consistently. This 2013 competition is one of many typing competitions across the Sinophone world. And what you often see is that the contestant who proves victorious is using a structure-based system, not a phonetic or input-based system. And this is for a number of really basic reasons. The basic reasons that, in fact, led many engineers to say that, yeah, we're aware of Hanyu pinyin. Hanyu pinyin has been around since the late 1950s. We're aware of it. We just think it's garbage. We think it's the worst of all possible ways to govern this human-computer interaction. And the chief reasons that the ceiling for this is lower than structure-based input is maybe fourfold. The first is that in Hanyu pinyin, there are many homophones. And so you could have the, I don't know, let's say the input sequence Li or something of that nature. Li corresponds to dozens and dozens of Chinese characters, because tone is not part of the input process really. And so what that means is it might be short and allow you, and it might be intuitive because the sound of it is intuitive to a Mandarin speaker. You are still then at the process of condemned to going through perhaps many pages upon pages of the input pop-up menu to get to the character you want, especially if the character you want is one of the medium or lower frequency characters. The other element of it is structure-based systems are artificial. What I mean by that is that people can, and they have, sat in their study for over a decade studying Chinese characters, kind of cutting them up into pieces, think of Lin Yutang, and they can create a series of totally fabricated artificial shapes in order to optimize their system. They optimize it for the not just the minimum number of say letters to arrive at a character match, but to arrive at a place where any alphanumeric string has the smallest number of matches possible. They want sort of taxonomic evenness to the system. When you're using Hanyu pinyin, you can't go back to the beginning of time and change the history of Chinese. Li is common, and Li is common, and there's not a darn thing you can do about it. And so there's a limit to the kind of engineering that one can do. You've got to kind of take spoken Chinese at face value and start from there. There are other more technical issues of nested codes. So if you're typing on a machine and you write LI, how does the computer know if you're done? Because there's also LIN is another valid Hanyu pinyin sequence. And then there's also LING. And so this is where the system has to do all of this kind of ex post facto disambiguation that is very computationally expensive at a time when processing power and memory are at a premium. And so all of this is basically discounting this. What saves Hanyu pinyin, despite the fact that engineers understand it to be, sort of the worst option, is first the movement from character at a time input to compound at a time input. So the kind of its greatest weakness, the inputting of a single Chinese character, can become kind of its strength, because now we have, for the example that I gave of anxuan, and we can just write AQ. If I write AN, good luck. I'm going to have to maybe scroll through some things. An is pretty common, but still, if I write xuan, I'm going to have to, but if I write AQ, then the system has a lot more to go off of and a lot smaller set of possible matches. And once you take these various shortcuts and abbreviations, and then you start compounding them with basically predictive text technologies and more advanced, things from basically machine translation, then suddenly it's like, this has a fighting chance. Once it has a fighting chance, then Hanyu pinyin has this massive advantage, which we don't talk about very often, which is the full budgetary backing of the government. If I'm going to teach you Wubi, if I'm going to invent a structure-based input system, I also have to start my own coaching, company. I've got to start my own publishing company. I've got to make manuals. I've got to teach people myself. Someone who is piggybacking on Hanyu pinyin doesn't have to do any of that work, because quite literally the education system teaches little kids Hanyu pinyin from the start, so we can offload that. But at the end of the day, and this is what many people don't kind of get about the Hanyu pinyin and pinyin input, is that pinyin input is built on the back of Hanyu pinyin, but they are not the same thing. In fact, pinyin input is in some cases a violation of the sort of rules and regulations of Hanyu pinyin. And I know this from a very sort of sweet and funny story, at least in my life, is when I first studied abroad in Beijing, I had to get a side job, and I was brought in to teach English in basically a preschool. And I walked in there, and there were these 50 adorable kids. I didn't have a lessons plan, so we did head, shoulders, knees, and toes for about an hour, and then I realized I needed to go out and get some textbooks for the next class. But one day I walked over to the blackboard, and I wrote a Hanyu pinyin phrase on it, and I accidentally put the macron over the wrong vowel in the diphthong. 50 kids chimed in simultaneously, like wrong, that's absolutely, that's not Hanyu pinyin. Hanyu pinyin has a strict rule and regulation about spelling, the placement of accents and so forth. Pinyin input is full of shortcuts and abbreviations and all of these things that, technically speaking, are not Hanyu pinyin. And that was essential to pinyin input's rise, was violating the rules of Hanyu pinyin counterintuitively. But at the end of the day, there still is a trade-off. We get pinyin input gets us massification, gets us doorways into wider usage. It offloads the education onto the government and the education system. But the total informational capacity of it is demonstrably slower than structure-based input. Oh, and it also solves the interest of nation formation and nationalism, because to use a Hanyu pinyin-based input system effectively, even if you're not fluent, if you're a Cantonese speaker who is not fluent in Mandarin Chinese, you have to know your way around standard Chinese enough to use it effectively. So it's also pinyin input becomes a mechanism of this very long-standing ambition of Chinese regimes dating back to the 19th century, which is unifying the spoken language, which is this dream of Chinese regimes since the end of the Qing dynasty. Yes.
Tom, I'll shout so
Yes.
others can hear me.
I can repeat your question too.
If you go back a couple slides on the Yanjiang, on the Zhonghua Renminbi
Yeah.
example.
Sorry, it's a little slow. Let's see, it's coming up. Let's see where it is. I don't think I have cursor control over that. Here it is. There we go. Yes.
Yeah. What year? What time is this?
This is the second half of the 1980s. So the question is what time period is this particular diagram of a Chinese computer monitor from? This is from basically the late 80s.
Late 80s.
Yep.
It's quite telling. The idea is there, but this specific example, I might be missing something for those who can read Chinese. Basically, it says you enter the word People's Republic of China already,
Mm-hmm.
and it predicts what you may need next.
Right.
And you do two kinds of predictions.
Right.
One is a unigram prediction,
Right.
and the other is a bigram prediction.
Right.
So that's 联想字 and 联想次数 respectively.
Right.
But in this case, none of them is right.
In terms
As far as
of
I can read.
and
I cannot
right.
find one that would actually follow
Right.
that phrase.
Right. It's doing it. So keep going. Yes.
The reason is that what it could do is predicting at bigram level.
Right.
It's only used the last character
That's right.
or as the pretext to predict what's going to follow.
Exactly.
It doesn't take the full string into account.
That's right.
And this is, by the way, what we have been doing
Right.
since then over
Yeah.
years. And also some of these, if user actually took them as prediction, it could be a disaster. For example, the last one, Mindang,
Mm-hmm.
because it follows the word guo quite common,
Mm-hmm.
quite often, Guoyindan, which means the nationalist party,
Right.
but it contradicts with People's
Right.
of China.
Right.
So therefore, it could not follow.
Right.
If you look further back into history.
Right. So the question, if you're for those joining virtually, that on this particular example of this lianxiang, this sort of connected thought next character prediction, that the prediction is being made not out of the entire phrase here of 中华人民共和国 of People's Republic of China. It's being basically made on the basis of the final character in that sequence of guo. But one qualifying point here is that what you're looking at is not that 中华人民共和国 has been inputted in one go. Presumably what has happened here is that originally the sort of composition window is blank. Someone has to enter the first character of zhong and has to do that just of using the input system at its disposal. But that the second that zhong was there, then the next series of predictions would have been there. And presumably, maybe hua would have been there, in which case the person does not have to enter the input sequence for hua, can just select it from the menu. And after hua, probably what things would have gotten wrong. Probably after hua, it might have been like hua xia or whatever it might be, that you would have to then continue the sequence because the prediction is being made based on the basis of really the last character. And because at this point, something like contextual analysis or sort of greedy algorithms or whatever it's going to be are not there yet. This is effectively, what you're looking at here is effectively a next dimensional digitization of the strategy that we saw on the mechanical Chinese typewriter tray bed. The main difference here is that in the physical world, if you're talking about a plane, if you imagine the Chinese typewriter Zipan as just a plane, the maximum number of neighbors is 8. The Moore's neighborhood is 8 characters. That's the maximum, unless you're at the corners. In this particular case, the number of adjacent characters can be increased because we're entering a sort of n-dimensional kind of mode here. So now a single character can have not just 9 neighbors, but can also have 9 plus these neighbors in the bottom. So it's the same principle, just like if you're making a natural language tray bed, you can't anticipate the next character based upon what the typist did. That's gone in history. It's only on a character by character basis. But from this point, then we are in fighting position to start saying, let's actually think of the longer context of the phrase, not just the last character, and move on. And incidentally, this is one place where Sino-Japanese computing interactions were really, really, really important because of the peculiarities of Japanese input, which have both kanji and kana, Japanese human-computer interaction had to pay a lot of attention to kind of contextual analysis to figure out, is the person trying to input kana? Should I convert this kana to kanji? Should I, having converted it to kanji, but then they added another graph and now I think it's kana again. And that after kind of normalization of relations in 1979 or the 70s with Japan, there's a lot of exchanges between Taiwan, China, Japan about the question of contextual analysis. And without that exchange, we don't have pinyin input either. You needed to get the math right of that in ways that structure-based input didn't require. Yeah.
That's super interesting. And many of us in the room online are part of that history. They are actually advancing it. And
awesome.
Advanced all that. One of them is Kabul. In the interest of time, Kabul, you asked the last question.
Yes, please.
We'll switch to the informal time of discussion. Yeah. Kabul, you can hear me?
Hello, hello. This is
you raise a hand.
Yes, yes. Hello, can you hear me?
Yes.
Hi, this is Carbo calling from New York. I have since you were talking about kanji, I have the question. So during the industrialization era, given that Japan industrialized before China did Japanese invent anything alternative to the Chinese typewriter? How did they type kanji?
Good question. Yes. So effectively, and it's interesting that in so many ways.
Let me repeat.
Let me repeat the question. So given Japan's industrialization in the 19th century, early 20th, before China, and confronting a comparable issue of kanji, is there an alternative in the Japanese context to, say, the Chinese typewriter? How do they deal with the question of kanji? And the answer is that Japan, and to a certain extent Korea, but especially Japan, has its legs in both worlds, which is a recurring theme, I think, in modern Japanese history. And quite literally, there are Japanese kanji typewriters, which are indistinguishable from tray bed-based Chinese machines. And there are kana typewriters, so hiragana or katakana typewriters that are indistinguishable and actually manufactured by Remington and Olivetti and others, because you can keep them, you can keep the Remington manufacturing plant the same and achieve Japaneseness as long as you do that. So they will end up having their legs in, astride in both kind of techno-linguistic worlds. And then in the era of full-blown Japanese empire building and Japanese colonialism, the leading manufacturers of Chinese typewriters in mainland China will be Japanese companies. And in fact, the double pigeon typewriter, the famous double pigeon typewriter that is, the PRC era typewriter, the emblematic typewriter, is a retrofitted version of a Japanese-built Chinese typewriter called the Wanneng. And basically in the early 50s, after Japan's defeat in the war, you have all of these various typing manufacturers that are basically building Japanese devices. They glom together and they say, we want to 仿造 or sort of retrofit or rebuild these Japanese built devices into the double pigeon. So the double pigeon machine is a Chinese-Japanese typewriter at the same time. And then these worlds will meet again, especially in the 1970s, with the era of some of these really foundational, very early international conferences on Chinese and kanji I/O and human-computer interaction and input, because again, Japanese computer engineers have to deal a lot with the kind of the math and the probability and the kinds of algorithmic analysis that Chinese engineers or those working on Chinese don't really have to worry about because of the predilection for structure-based input rather than phonetic input. Once you go phonetic, and this is really interesting, the entire labor force of the input world changes. In the world of structure-based input, you can be a sort of eccentric retiree with a Kangxi dictionary and 15 years on your hands, and you can analyze characters. Well, you can live this sort of literati life, and you don't have to know anything about computer engineering, about anything. You can find a hotshot kid to program it for you after you're done. In the realm of phonetic input, you basically have to be an applied, you have to have applied math, you have to know probability theory. The era of the charismatic inventor is gone. I mean, there's no charismatic inventor of SOGO input. There's no charismatic single inventor of Microsoft input. This is now, team-based. And so this changes dramatically, and Sino-Japanese connections right there are really, really important. Thank you so much for that.
Thank you, Professor.
Thank you so much.
Thank you. Thank you very much.